right, everyone. Before we get started on the Chapter 12 stuff that we need to talk about, I want to do a little bit of discussion about some topics from Chapter 11 that we haven't discussed explicitly yet, but we're in the pencast and some other things. And so we've learned about making epoxides, which are an ether that have particular reactivity. And why do they have particular reactivity? Why? They have ring strain, that's right. So we can take an epoxide, for example, something like this, and we can open up that ring because of ring strain by a variety of nucleophiles, right? And so if we use a nucleophile under basic conditions, and I'll just any generic nucleophile at the moment, which of those two carbons will get attacked by the nucleophile? The least substituted. Under basic conditions, it's always the least substituted because of steric hindrance, right? So we know that under, and I'm going to put it in quotes, basic conditions, meaning no acid around, right, we're going to ring open the epoxide at the least substituted carbon. And then, of course, after workup, we would get something like this, right? Now, if we're under acidic conditions, let's say HCl, which carbon atom gets ring open, or does the attack occur at? At the more substituted carbon atom, right? And so we would end up with that particular chlorohydrin, because the chloride would function as the nucleophile. Why is it that under acidic conditions we see nucleophilic attack at the most substituted carbon? Isn't that the most sterically hindered place? Right? It would seem to counter this observation. So why is it? Yep, not Markovnikov here. It's the weakest bond. Because in the first step, when we have an oxygen atom under acidic conditions, what happens to that oxygen? It becomes protonated, right? And so that's going to make this more substituted carbon-oxygen bond the weaker bond because it's trying to break already, right? Oxygen doesn't like to be positively charged. And so your nucleophile will actually attack the most substituted carbon under those conditions. It's very important for you to remember, under basic conditions, the nucleophile will attack the least substituted. Under acidic conditions, it will attack the most substituted. How would I make that epoxide? How do we make epoxides? Okay, we can take an alkene. In this case, what alkene do I need? If we look at it, how many carbons? I need 3 carbons, right? That's the 3 carbons here. I'm on just a number 1, 2, 3. 1, 2, 3. So really what we're doing is we're adding an oxygen atom across an alkene, right? A single oxygen atom. What reagent do we use to do that? It's not water. What reagent can do that? Starts with a P. Close. Peroxy. It's a peroxy acid. And there's one in particular that I'm fairly fond of. It's metachloroperoxybenzoic acid, MCPBA, another acronym. Okay? So if you have metachloroperoxybenzoic acid, and an alkene, you will get an epoxide. Can anybody tell me which of those oxygen atoms in the peroxy acid actually ends up being incorporated into the epoxide? do you think, Jamie? All the way to the right, the end one. That is correct. That particular oxygen atom is the one that ends up being incorporated into the epoxide. It's a concerted reaction mechanism. The arrow pushing is kind of complicated. I'm not going to hold you responsible for that. What I want you to know is that a peroxy acid, okay, any carboxylic acid with an extra oxygen, basically, plus an alkene will give us an epoxide, okay, through a concerted process. Now, this turns out to be kind of important because if I start off with a transalkene and I use MCPBA, what's my product going to be? It's going to be an epoxide, but what's the stereochemistry going to be? Yeah, those two methyl groups are still going to be trans to one another. If I start off with a cis-alkene, what's the stereochemistry going to be? It is. It becomes cis. The two oxygens are on the same side again. I'll show them coming out of the board at us. This is a stereospecific reaction. The stereochemistry of the alkene is retained in the epoxide. So if you want two groups to be trans to one another, those two groups have to be trans to one another in the alkene. If you want them to be cis to one another, they have to be cis to one another in the alkene. Okay? Now let's do a little thought experiment. Let's say that Gabby's going to come to the lab and she wants to do a reaction where she does a Williamson ether synthesis. Okay? And so she starts off with, oh, I don't know, let's say this alkyl halide, and she's going to mix that with sodium methoxide. And she's going to get the reaction to go to where she, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Plus sodium bromide, right? Williamson ether synthesis, it's an SN2 reaction. We've studied this a number of times, right? Nucleophile comes in from the back, displaces the halogen. We've got a good leaving group, everything's set up for SN2. There's a problem with this reaction, though. Can anybody tell me what it is? It's probably the best example I came up with, but it'll work. What's the sodium methoxide soluble in? Water. What's the alkyl halide soluble in? Water. Not water. That's right. So we've got an issue with having things that are not going to be miscible with one another, right? And so how are we going to get this chemistry to work? Well, we have to use what's known as phase transfer catalysis, PTC. Phase transfer catalysis. So if you think about that name, phase transfer catalysis, what does that tell us? Okay, so it's going to be catalytic. I don't need a whole bunch of whatever I'm going to use, right? And it's going to allow things to cross the phase barrier. Let me use just a little bit of a better example here. You okay? Yeah. All right, you're good. That's good. 1, 2, 3. No, she's not. No. So we're doing this chemistry, SN2 chemistry again, right? So Gabby figures out that sodium cyanide is going to be soluble in water, so she dissolves it in water, right? And let's imagine we've got a beaker here that she's going to run the reaction in, okay? And so she adds into it water plus the sodium cyanide, and then she adds in the alkyl halide. How many phases are we going to have? I'm missing what? That's 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. No. Alkyl halides at all, are they soluble in water? Not at all, right? There's no OH. Okay. So we need a way to do what? When we mix this all together, we're going to have this lower organic layer because she took this and she dissolved it in something like methylene chloride, which is dense, right? And above, there's this aqueous layer that contains the water and the sodium cyanide. So up here, we have cyanide as the nucleophile, and down here we have the alkyl halide as the electrophile. And they aren't mixing with one another, right? They are phase separated. So what do? We're going to add a phase transfer catalyst that will allow us to transfer the nucleophile from the organic layer, from the aqueous layer into the organic layer. How do we do that? How can we do that? Oh, that's right. So I've got sodium cations and cyanide anions, right? But what happens if I add a cation that's actually organic and aqueous soluble? One of the things that we can add to this are what are known as quat salts, where R is just some alkyl chain. It's a salt, so it is somewhat soluble in water, but it has an organic stuff on it around the nitrogen, right? So it's also going to be organic soluble. So what happens when we add this in, how does it work? It doesn't actually emulsify it. You can do emulsion type chemistry, but this one won't do it. So when I add a little bit of this to this mixture, what's going to happen to this? Some of this is going to be in the water layer, and some of this is going to be in the organic layer. So how does that help? When this is in the water layer, all that has to happen is whatever the halogen is here, right? Let's say this is the ammonium chloride. Well, that's X minus, right? But can't that just exchange with cyanide? That'd still balance the charge, right? And so when I have that exchange happen, what can happen with that salt? If the cyanide gets exchanged for X, what happens? It becomes more soluble in the organic layer. That's right. And so it can actually transport the cyanide into the organic layer where it does what? It reacts, right? And when it reacts, you get the bromide anion. This goes back up into the water layer, it exchanges some more, and this can go back and forth, right? So this, yeah, it is very much so like an equilibrium kind of thing. And it turns out that this quat salt, as we call them, can transport aqueous soluble anions into the organic phase. That's what it does, okay? Now it turns out that this is kind of a special thing for me because it was actually developed at Phillips Petroleum. I think it was Phillips or Conoco. But anyway, either way, it was an Oklahoma company. And so this was a lot of stuff that we talked about when I was a graduate student at Oklahoma because phase transfer catalysis was developed in the state. In the petroleum industry, they needed phase transfer catalysts to do a variety of the chemistries that they were doing. Okay? So what you need is you need a cation that can be soluble in both layers and can transport your nucleophile from one layer to the next. That's how phase transfer catalysts work. So when you have two things that look like they're never going to mix, you just got to bring something in that can help bring the two together. Any questions about that? You have something, Debbie? Do you have a question? QUAT. All right. Today we're going to talk about oxidation and reduction in organic chemistry. Okay? It's going to give us another way in which we can make alcohols, and it's going to give us a way that we can actually take alcohols and convert them into other things, whether we're talking about oxidation or reduction. Okay? You all should be building road maps if you're not. This is an example of a road map for just an alkene. And at this point, okay, we're just in chapter 12 now, but this point, you can do all these things to an alkene right now. That's a bigger set of tools than you thought you probably had, right? We can take an alkene to alcohols in an anti-Markovnikov fashion. In a Markovnikov fashion, we can make syn-diols, we can make anti-Markovnikov alkyl halides, we can make Markovnikov alkyl halides, we can make alkanes, we can make halohydrons, we can make dihalides, and there's probably a few more that we can put on there. I promise you this is the easiest way in the world to keep track of what your functional group transformations are. Right now you can look at that and you can go, the functional group transformation for an alkene, I can make an alkane, I can make a diol, I can make a halide, I can make an ether, right? I can make a dihalide, the whole 9 yards. It allows you to recognize immediately what kinds of functional group transformations you can easily do, okay? Here's some example problems that I want you to work on your own, okay? This isn't for credit, but they are a little more challenging in the sense that there's no direct way to do what I'm asking you to do here, but you have all the tools in your toolbox to do it. Next week, I will post the answers outside my office up here, and you can come and take a look at them. So what's going on here? What's the functional group transformation in this first one? It doesn't change, but what does change? The position. So it's a functional group translocation or transposition. Have I taught you how to take one alkene and put it into the next one? No. But you have every tool in your toolbox to do that. You can do that. Okay? There's no direct reaction. So think about it. What do you know that you can do to alkenes? You can add things across them, right? And maybe then I could add something and then eliminate to get back to my alkene. Think along those lines. Okay? Do we know any way to where we can take an alkene to a dihalide that looks like this? What's unique about this? I've got a bromine and an iodine, and they're syn to one another. They're not anti, right? That's weird, but you can do it, okay? And what about this? Am I doing a functional group transformation? Doing a translocation or a transposition. That's right, I'm taking an alcohol from one position and putting it somewhere else. You have every tool you need to do that. Okay, I just haven't explicitly taught you how to do that. And then in this last one, you're doing a couple of steps. Okay, so keep them in mind. Work on these, okay? Don't just take it as something extra to do. These are challenging. I want you to think about them. These are the kinds of things you need to be able to think about when test 1 comes around, okay? So it's some good practice for how you're going to have to think about using the tools that you have in your toolbox to do things that you haven't seen before, okay? That's what a real chemist does. They take their tools that they have and apply it to new problems, okay? When we go into the research lab, it's a new problem. Nobody's ever done it before, right? If somebody has done it before, it's not worth doing. Been done, right? And the cool thing about that is, and one of the things I like to tell my students when they're doing research and they've made a new compound, one of the neat things that I like to tell them is that, you know, more people have walked on the face of the moon than have just done that. That's kind of cool, right? When you're the first person to ever make something, that's cool, okay? And that happens every day in our research labs, okay? People are doing things that have never been done before, okay? All right, so let's talk a little bit about oxidation and reduction. And in the context of this particular set of transformations, we're going to really be focusing on the carbonyl group. You remember that the carbonyl group is the C double bond O, but it can belong to the functional groups of aldehyde, ketone, carboxylic acid, ester, amide, so on and so forth. I'm just showing these, right? All of them contain the carbonyl. What do we know about the carbonyl reactivity? Are all the bonds strong? In a carbonyl, are all the bonds strong? How many bonds does it have, Sam? Between the carbon and the oxygen? 2. And what kind of bonds does it have? It's got a pi and sigma, right? So which one's strong, which one's weak? pi is weak. That's right. So we're going to be exploiting this weak pi bond in some of this chemistry. So for example, if we look at an alcohol, all we have to do to convert that into a carbonyl is remove what? No. To go from the alcohol to the carbonyl, I have to remove hydrogen, right? How many hydrogens? I have to remove 2 hydrogens. So if I remove this hydrogen and this hydrogen, I can get a carbonyl. That, by definition, is an oxidation process. In organic chemistry, oxidation results in the removal of hydrogen from a molecule or an increase in the number of bonds between carbon and electronegative atoms. Now, we're going to calculate oxidation numbers, but organic chemists don't like to do that. We just like to look at something. Am I losing hydrogen? If I am, I'm doing an oxidation. And the reverse of that must be gaining hydrogen, which is a reduction. That's right. So here I'm removing bonds to hydrogen, so that's oxidation. Here I'm adding bonds to hydrogen in the reverse. That's reduction. Both of these reactions can occur. I can take alcohols to carbonyls, and I can take carbonyls to alcohols by judicious choice of reagent that I use. You're going to learn a couple of oxidants and a couple of reductants that'll do these types of reactions.
You said oxidation is literal hydrogen molecule, or a decrease in the number of bonds?
Well, a decrease in the number of bonds between carbon and hydrogen is also considered an oxidation. Yeah. We know that the carbonyl compound, or the carbonyl part of a compound anyway, right, is going to be trigonal planar because this is an sp2 hybridized center. We know that the carbon and the oxygen, that bond is polar because oxygen's more electronegative. That means that this carbonyl is going to have a partial positive charge associated with it. Okay, we know that the bond angles are about 120 degrees, right? And so all that's going to be relevant when we start talking about some of this chemistry. Just a little refresher there. Okay. If you think about a carbonyl and an alkene, your first instinct is to sit there and go, those are very similar, right? Because an alkene has a sigma bond and a pi bond, just like a carbonyl has a sigma bond and a pi bond. But there's an important difference between the two. And that important difference has to do with the fact that the bond is polarized. An alkene really isn't a polar bond, right? The 2 carbons are identical for the most part. Okay, but here we have clearly different atoms with different electronegativities. And so even though this is a minor contributor to the overall resonance hybrid, it's relevant. Okay? And so we should be able to exploit the fact that the carbon is actually electron deficient and use that so nucleophiles can attack the carbon of the carbonyl. Okay? And so we'll play around with that in chapters to come as well. Okay? So one of the things that you need to know for just nomenclature purposes, when you see O in brackets like this, that means general oxidation. When you see a hydrogen in brackets, that means general reduction. What do I mean by that? General. What do you think I mean by that, Mason? If I told Jamie to go in and do a general oxidation, I'm telling her to oxidize something in a general sense. I'm not telling her what to use to do it, right? So when I write O in brackets, I'm just saying an oxidation is occurring, but I'm not telling you what reagent we're using to do it. Maybe it's molecular oxygen. Maybe it's an oxidizing agent that we have to buy, okay? There are many different types of things that can do that. And so these are just general symbols that mean oxidation has had to occur and reduction has had to occur if you look at the bottom one, okay? So calculating oxidation states in organic chemistry is pretty straightforward, very similar to how we calculate formal charge, with one exception. In formal charge calculations, we always assumed equal sharing of the electrons, right? In oxidation state calculations, you cannot make that assumption. Electrons will be unequally shared, okay? So if we're looking at a molecule like this, we know, based on electronegativity, that oxygen's more electronegative than carbon, so which Who gets these electrons? Who do they get assigned to? To oxygen. That's exactly right. In formal charge, we would have assigned one to each, right? Because we drew the circle and we would have just made the assignment. Okay, so carbon has obviously a formal charge of 0 here, but it does not have a 0 oxidation state. Okay? And then you just simply take the valence electrons for the particular atom minus the assigned electrons, and that gives you the oxidation state. So let's look at this. Okay. Those yellow electrons, as I have them drawn, completely belong to oxygen. Okay? What's the electronegativity difference between carbon and hydrogen? Which is more electronegative, carbon or hydrogen? Carbon. It's slight, but it's still... So those electrons completely belong to carbon. How about here? Only one electron belongs to carbon. Why is that? They're equally electronegative, okay? And so we know that carbon comes in with 4 valence electrons, and we're going to assign to it 2 here, 2 here, and 1 from here, right? None of these get assigned to... So how many do we have? 2, 4, 5. So that carbon in ethanol has an oxidation state of -1. That is not its formal charge. That is its oxidation state. Okay? So, is that a highly reduced form of carbon or not? It is not a highly reduced form of carbon. You're correct, Gabby. Give me an example of something that would be a highly reduced form of carbon. Something simple. Methane. Bingo. Methane is a very highly reduced form of carbon. What would the oxidation state of a carbon be in methane? -4. That's exactly right. Okay? So ethanol, I don't know why I keep calling it methanol. Ethanol the carbon is reduced in a reduced form because it's negative, but it's not the most reduced form that we can have. Okay? So, real quickly, tell me what the oxidation state of the carbon atom is in methanol and the oxidation state of the carbon atom in formic acid. The thing I always liked about organic chemistry, you just have to do basic arithmetic. No calculus, no trig. Rose, what do you think the oxidation state of the carbon atom is in methanol? Very good. And then you calculated that based on 4 electrons coming in from the periodic table for carbon, and then you subtracted how many from it? 6, because the CH bonds, which there are 3, all those electrons belong to carbon. The carbon-oxygen bond, all those electrons belong to oxygen. So we have the carbon atom there in the -2 oxidation state. So is that alcohol carbon the same oxidation state as the alcohol carbon in ethanol? No, they are in different oxidation states. How about for formic acid? What's the oxidation state? It is +2. Okay? And it's pretty easy to see that that carbon atom has to be more oxidized than methanol, right? Just by looking at it. Why? It has more bonds to oxygen. That's exactly right. I look at this and I go, well, this carbon atom has 3 bonds to oxygen. 1, 2, 3. This one only has 1. I know this has to be in a higher oxidation state, more oxidized, if you will, than that one. And for the most part, that's going to serve you well, just being able to identify that without having to go and calculate oxidation states. You know, in general chemistry, we spend a lot of time having you calculate things. And there's nothing wrong with that. You need to know, I mean, there will be times in your career where you need to know something absolutely. But in general, you need to be getting a feel for just looking at something and recognizing oxidation state compared to something else. You know, when you're in the lab working in your polymer lab, your biology lab, at some point you'll be going, well, that's in a more oxidized state than that, and that's going to drive how you think about that problem. And you really didn't need to sit there with your calculator and figure anything out. You know by looking at it where it stands. Okay? In a way, it's kind of like speaking a foreign language. You get really good at it, right, when you no longer have to do the conversion of the words in your head. Right? That's how you know you're good at it. And so when you start to be able to look at molecules and recognize these features without having to think about it too hard, that's when you know you're starting to get the skill sets that we really want you to have by the time you leave this class. Not that you'll be completely there, and it's okay, right? But you should start getting there at this point, okay? One of the things that we can do with carbonyl compounds, and I'm going to pick on an aldehyde here, is we notice that nucleophiles can actually attack the carbon of the carbonyl, go through what we call a tetrahedral intermediate, and actually give us an addition product that's an alcohol. And that makes sense. Why would a nucleophile attack the carbon of the carbonyl and not the oxygen of the carbonyl? Because the carbon's partially positive, and the nucleophile is either negative or partially negative. That's right. Opposites attract. So the nucleophile attacking the oxygen makes no sense because the oxygen atom has what? Has a partial negative charge, and also it has what? That aren't explicit. Well, no, they are explicitly drawn up there. Lone pairs, right? So if you're negative, are you going to want to go around lone pairs? No, because like charges repel, right? This is a common mistake of students. They will have the nucleophile going to the oxygen because they go, well, the oxygen's more electronegative. It should want the electrons. Not in that sense, because you're taking the electrons from the nucleophile and trying to get them around the lone pairs. That's not how it works. Remember, oxygen only wants the electrons from the bonds that it's participating in, not from some outside reagent, okay? Like a nucleophile, okay? This is a pretty simple mechanism. The nucleophile attacks, and what bond are we breaking here? The weak pi bond. We get what's known as a tetrahedral intermediate. This reaction goes to the right because I'm breaking a weak pi bond and I'm gaining a strong sigma bond, so that's favorable, right? This is now a base, and it just stays there until we dump the reaction on water, and water will give up one of its protons because this is a stronger base than hydroxide, and you end up with the alcohol. So, you all now know a new way to make alcohols. I can take aldehydes or ketones and I can make alcohols by the addition of nucleophiles. You now have a new tool to put in your toolbox. Okay? And we're going to talk an awful lot about what types of nucleophiles we can use to do this particular reaction. Okay? There are one type of nucleophile that we call the hydride, H-. That can function as a nucleophile, and there are two reagents that work really well for this. Sodium borohydride, which we've seen before. Where did we see that before? Where did we see that reagent before? Its cousin was in hydroboration, BH3, but this is BH4, right? This is sodium borohydride, not borane. We did, and what did we use it to reduce? Remember the demonstration I did, the mercury rain? That was the second step, remember? That was the demercuration step. It was a reducing agent. It is a reducing agent, sodium borohydride, okay? And boron is a metalloid, and aluminum is a metalloid, right? And it turns out if you look at the electronegativities, hydrogen is actually a little more electronegative. So the hydrogen is pulling the electrons to itself from the metal. And so these behave as if they are H-. There is no H- floating around in solution, and that's very important to understand. But we can think about it as H-, okay? And so when we take an aldehyde, in this case, or ketone, doesn't matter, but if we take an aldehyde and we treat it with either sodium borohydride or lithium aluminum hydride, followed by typical workup, we're going to get an alcohol. If I take an aldehyde and I reduce it with sodium borohydride, what kind of alcohol do I get? What do you think, Brian? If I take an aldehyde and I reduce it to an alcohol, what kind of alcohol would it be? It would be primary. If I take a ketone and I reduce it to an alcohol, what kind of alcohol do I get, Delaney? If I take you're stressed out? Oh, spaced out. Don't stress out on me. Don't space out either. If I take a ketone and I reduce it to an alcohol, what kind of alcohol would I have? Primary or secondary? Secondary alcohol, that's right. I'm not doing anything to those carbon bonds, right? I'm just messing with the carbon-oxygen bonds, right? And so I can get primary and secondary alcohols. And officially what I'm doing is adding H2 across the pi bond. It's a reduction, right? I'm adding hydrogen to the molecule. It's a reduction, okay? But one of the hydrogens comes from the hydride and the other one comes from water. The hydrogen that is attached now to the carbon in the product came from the hydride, and the hydrogen that's on the oxygen comes from the water. It's a two-step process, but it's real easy to do. Have you all done the reduction yet of the ketone in the lab? Is that happening this week? This week? Solid phase extraction, so it'll probably be next week then. Can't remember when. Well, it won't be next week because you guys have Mardi Gras, right? Yay, Mardi Gras. Yay. Okay, so anyway, let's look at the mechanism. And I want you all to help me out with this. So let's say we take acetaldehyde and Gabby comes in the lab and she throws in sodium borohydride and she adds water. The product that she's going to get is ethanol. How does that work? We know that the boron-hydrogen bond is polarized, right? And which atom gets more of the electrons? The hydrogen or the boron? The hydrogen, that's right, because the boron's a metalloid, right? So we're going to be pulling towards the hydrogen. Hydrogen's a little more electronegative. The way that I approach these problems is I think of sodium borohydride as 4 moles of H minus. And I'm going to put it in quotes because it's not really H minus floating around. Okay? Now, Matthew, based on that, how would I do the mechanism? What's my nucleophile? Hydrogens or hydrides? Hydrides. And how would I push the arrows? Yeah. And? Okay. And so I just formed a new carbon-hydrogen bond, right? And I end up with this, which then upon treatment with water, which it's in, gives me the methanol, or the ethanol. The mechanism is identical for lithium aluminum hydride, with one caveat. If you ever write lithium aluminum hydride with water in the same step, it's wrong. Can anybody tell me why? You're really close. Has nothing to do with the lithium itself in this particular case, but it does go boom. I can take sodium borohydride, place it in water. I did that for you all. Nothing happened. If I came in and I added lithium aluminum hydride to water, we would have a big fireball on our hands, even a small amount. Okay? Lithium aluminum hydride despises water. This is why we do not have you all working with lithium aluminum hydride in the laboratory. We have you working with sodium borohydride. Because you all would have your facial hairs all singed off, your eyebrows would be gone. Okay? Huh? Lithium aluminum hydride you have to do in 2 steps. The first step is without water, and then once the reaction is over and you're confident that all the lithium aluminum hydride has been consumed, then you add water. Okay? So if we look at this, we notice that we can take an aldehyde and do a general reduction. Why am I using general reduction here? Because I'm not telling you which reagent does the chemistry yet, right? An aldehyde goes to a primary alcohol. Ketone goes to a secondary alcohol. But notice a carboxylic acid and an ester both go to primary alcohols. We'll talk more about those mechanisms later, okay? The important thing that you need to know is that everything will be reduced to a primary alcohol with the exception of ketones. That's easy to remember. All of these functional groups will be reduced to a primary alcohol with the exception of ketones. Okay? Now, what you're going to use to reduce an aldehyde versus a carboxylic acid is not the same reducing agent. Okay? You have to know which reducing agent to use where. And that's going to be the thing that you need to pay attention to. So let's look at some examples of reduction by sodium borohydride. We have an aldehyde, sodium borohydride and water. What's my product going to be? Before I draw it up there for you, what's it going to be? Ethanol? It's going to be propanol, and it's going to be a primary alcohol, right? That's right. So we end up with one propanol. If I take cyclopentanone and do this reduction, I'm going to end up with a secondary alcohol, cyclopentanol. Okay? Ooh, now I've got two functional groups. I've got a ketone and an ester, and they're going to use sodium borohydride and water. In this case, they're going to add a little methanol and make everything better soluble, but that's okay. Alcohols are fine. What am I going to get now? An alcohol? Two alcohols? Three alcohols? Possible. Turns out we only get one alcohol. What happened? What got transformed and what didn't? So tell me what functional group that is. The ketone got converted to what? A secondary alcohol, and the ester was unchanged. Very good, right? Sodium borohydride is selective for aldehydes and ketones. It leaves carboxylic acids and it leaves esters alone for the most part. I can give you some examples where it doesn't behave well. But for your purposes, for the purposes of this class, sodium borohydride is a weak reducing agent. It will not reduce esters and carboxylic acids. Okay? So Jamie Lou comes in. She wants to do a reduction of this particular ketoester, as we call it, because it's got a ketone and an ester. She wants to do chemistry on the ketone and leave the ester alone. She's going to go looking in my lab for the bottle of sodium borohydride. And she'll be able to do this chemistry no problem. Okay? Now let's look at what lithium aluminum hydride does. Okay? Notice how they have it written here. They have it written as step 1 and step 2. Very important. Ignoring that is wrong. If you did it like this, you'll have a fire on your hands. So you take a ketone, lithium aluminum hydride, and ether without any water around. You let the reaction go, and then you quench it with water. You get a secondary alcohol. That's the same chemistry as with what? Sodium borohydride. Now, if I take an ester, lithium aluminum hydride will reduce this to two alcohols. This alcohol comes from this carbon-oxygen bond, and this alcohol comes from this part of the ester. So we're actually splitting the ester into two alcohols, okay, basically. And we'll talk about the mechanism of that later. But notice here, what's happening? It's reducing both of them. That's exactly right. Plus, we also get a molecule of methanol that's not shown there. But that's right. Lithium aluminum hydride will reduce esters. It will also reduce carboxylic acids. So Sarah comes into the lab and she wants to reduce an ester. What bottle is she going to be looking for in my laboratory? Lithium aluminum hydride. Brian comes into my laboratory wanting to reduce a ketone. What would be your first choice? sodium borohydride because it's safer. It's also a lot cheaper, right? So just some practical things there. So let's talk, we got just a few minutes, let's talk about the mechanism in the reduction of an ester with lithium aluminum hydride. So let's take a simple ester, ethyl acetate, which is commonly available in all laboratories, and we're going to reduce that using lithium aluminum hydride. And by the way, lithium aluminum hydride is always abbreviated as LAH, followed by water. We've got to be correct about it. We're going to end up with 2 molecules of ethanol. Bless you. Lithium aluminum hydride we can think of as H-. It's just a stronger H- source. So Katie, how do I push the arrows? Of the carbonyl, right? That's right. And so I end up with this is an intermediate, right? I have no water around to protonate that, do I? There's no water in this first step. Here's what happens next. This oxygen with its anion, those electrons come back down and reform the pi bond. But can I do that? Not without kicking something off. And it turns out that what you kick off is the alkoxide. And so I get out of that an aldehyde plus ethoxide. What do we know happens? What happens with aldehydes in the presence of lithium aluminum hydride? They get reduced again. And then these at the very end, when we add the water, give us the final products. This tetrahedral intermediate that we get collapses because we have a relatively decent leaving group on there. It's not great, but it's okay. Okay? So you do an addition, which then eliminates to give you an aldehyde, and that aldehyde is actually more reactive than the starting ester. So once it's formed, it immediately reacts with the lithium aluminum hydride. Okay? And that's how these reactions occur. So I'm going to stop here for today. I need your inverted lectures. Just turn them in.